Hello everybody, this is Rudra Pradhan here. Welcome to Engineering Econometrics. Today we will continue with linear regression modeling, that to the structure of simple regression modeling, and in other words it is a structure of bivariate econometric modeling. In the last couple of lectures we have already discussed the issues of regression modeling, that to with respect to two variables, where one is treated as a dependent variable, the other one is treated as a independent variable. And we have gone through the kind of structures, how to build the model, bivariate model, and how to estimate the model, and how to empirically test a particular problem. The way we have discussed is it's mostly the derivation of the parameters corresponding to the availability of dependent variable, independent variables, and the kind of data. And for instance, the with two variables y and x, the regression modeling simply represented as y equal to alpha plus beta x, and against by Wallace mechanism and with the help of availability of data, we like to estimate the model, and that to know the values of the parameters alpha and beta respectively. And after knowing the parameters, then we will have a kind of regression line, that is the estimated lines, or it is called as a line of the best fit. And on the basis of that estimated line or line of the best fit, we like to predict y with the availability of x, or any value of x you can predict y, since we have the information about alpha and beta. But the issue is that having the data and the identification of dependent variable and independent variable, and with the application of Wallace technique, we can get the estimated values, that is alpha hat and beta hats, and for that we can go ahead with the prediction and forecasting. But the structure of econometrics is that we have to test the model before you use the model for any kind of prediction and forecastings, whatever may be the engineering problem. So, once we have the estimated model, even with the values of parameters, that is alpha alpha hat and beta hat, and we like to test the model, and then we have to validate that the particular estimated model is a good one or best one and free from all kinds of errors, and after that we can go ahead with the prediction and forecastings. Of course, we have gone through some standard checks by obtaining the error term, which is the difference between the actual and the predicted, and with the help of these error terms, we like to verify certain things, that some of the error terms should be equal to 0, and error variance should be homogeneous in nature. There should not be any kind of heteroscedasticity issue. So, the model can be used for prediction and forecasting, but only checking the sum of the error and the error variance, it is not enough to justify or to say that the model is the best one or the line is the best one to go ahead with the prediction and forecasting. So, what are the things we are supposed to check, that we will discuss today, and after knowing all these things, then we can extend this model in the context of multiple regression modeling and multivariate regression modeling. So, the standard structure is like this. So, once we get the estimated model, so we have to go through the following test procedure. So, first one is the specification test, second one is the goodness fit test, third one is the diagnostic test, and fourth one is the out of sample prediction test. Of course, in the last lectures we have used this software, that is the Excel data analysis package, to obtain these parameters, and including these parameters, we have gone through so many other outputs. For instance, if you go through this particular problem, so this is the problem which we have actually analyzed yesterday. That is what actually we like to justify. Once again, I am highlighting how we have obtained these regression results. So, put just click data analysis, then the package will appear. So, just put OK on regression, then the box will appear like this, and so the box will the box will ask to put y indication and x indication, that is the range. So, here the second one is the y range, and we have to highlight the particular cost factor, and then we have to put the passengers numbers, and then allow the software to go ahead. So, we like to report all these items, and then we put OK, and obviously, then we will get the results like this. So, this is what the standard result which we have obtained in the in fact, last class we have obtained this and we have discussed, and now we will go more about this these results. So, up to last lectures we have discussed this much only. So, that is how to obtain the parameters. That means, technically for a bivariate model. So, we have y equal to alpha plus beta x, and then we will introduce error terms epsilon, and on the basis of estimation we will get estimated equation, that is y cap equal to alpha cap plus beta cap x, and by the way error term will be removed in the process, and where alpha head we have here alpha head, that is the intercept coefficient, which is equal to 1.5 round figure 1.57 plus beta head equal to 0.041. So, 0.041 and x. So, this is the alpha coefficient and this is the beta coefficient, and this is the x which is independent variable, and y head is the dependent variable predicted, and y minus y head will get the error component, which is nothing but y minus y head. And that is how in the extreme below you will find the kind of this is what the actually predicted, and that means technically the predicted equation equal to 1.57 plus 0.04 x. So, now for every x, if you put x value, and then you will get y head value. So, as a result, for every x we have a y predicted, and then for every x we have actual y, and the difference by default will give you the error terms. This is how this series, we have 12 samples, and for every samples we have a predicted value, that is for y, and again we have actual y. So, the difference will give you the residual component, this part, and so this is what it is called as a standard residuals, and of course, so the residuals will give you some kind of signal. Just you can put equal to sign and cross check whether this sum will be appearing 0 or not. So, this will give you some kind of indications how to obtain this particular component. Okay, so this is what the process, but ultimately in fact last class we have already discussed the sum is coming actually close to 0, and what will we do here, we like to validate these models by using all these test structures whatever we have discussed right now, that is a specification test, goodness fit test, diagnostic test, and out of sample prediction test. In fact, out of sample prediction test is the kind of structure mostly used for time series kind of modeling, and that means technically when your data is with respect to time series, then out of sample prediction test is somehow mandatory, but in the case of cross sectional kind of estimation or cross sectional kind of modeling, we may skip that particular out of sample prediction test. So, what is more important is to go through specification test, goodness fit test and diagnostics test. The first one is the specification test, which is more or less connecting to these parameters alpha head and beta heads, like for a bivariate model alpha head and beta head are the two pillars. So, the first check, that is the specification check or specification test, is to use to justify that the value of alpha head and beta head are significant one to go ahead with the kind of prediction. So, ultimately, so the value of alpha head and the value of beta head need to be tested whether they are statistically significant. So, so when we talk about specification test or something like goodness fit test or diagnostic test or out of sample prediction test. So, we have some we have step by step process to proceed, and then we will give a kind of signal that the model is free from all these obstacles. So, the standard procedure for specification test is nothing but going for hypothesis testing and to test that the particular parameters is statistically significant. That means, alpha head need to be statistically significant and beta head need to be statistically significant. Since it is a two variable case, so we are supposed to check only the significance of alpha head and beta head, and where there is no question of any compromise. So, it is question of yes no, because there is only one parameter which can actually validate the model, that is the beta, and alpha is the intercept which may not have so important for the time being, but beta coefficient is more important because it indicates the impact of x on y, and whatever the impact or and the kind of cause will go to y. So, that should be statistically significant, otherwise that particular variable cannot be considered as the primary variable or the most important variable to analyze the particular engineering problem. So, ultimately the procedure of hypothesis testing is to start with the formulation of null and alternative hypothesis, and then we have to select a test statistics. For instance, in the case of specification test, our objective is to test the parameters alpha and beta. So, obviously, the null hypothesis will be simply H0 where alpha head equal to 0, and again for beta it is a beta head equal to 0. Then to validate this particular statement, so we like to use t statistics, and then we like to calculate t of alpha head and t of beta head, and then we have to check whether the particular value is statistically significant or not. So, that means first you have to formulate the null hypothesis, and then the choice of the test statistic. In the case of specification test, we specifically use t statistics, and then we like to fix the probability level. So, we can fix at a 1% level, 5% level and 10% level. So, on the one side we have to report calculated t statistics, and then on the other side we have to report the tabulated statistic on the basis of the probability level 1%, 5% and 10%. So, the that is called as a critical value or tabulated value. The critical value and tabulated value specifically depends upon three things, that is the probability levels at 1%, 5% or 10%, and then the degree of freedom which exclusively depends upon the value of n and k, that is the sample size and the number of variables or number of parameters in the system. So, so we have to go to the t tables, and then corresponding to the degree of freedom and at a particular probability level, you have to find out the critical value. So, that is one side of the game, and the other side of the game we have to report the calculated t statistic, which is nothing but actually a T alpha, it is called as a T alpha heads, which is nothing but alpha head by standard error of alpha head, and then for T beta head. So, it is beta head divided by standard error of beta head. So, ultimately we need to calculate standard error of alpha head and standard error of beta head, and that is nothing but square root of variance of alpha head and square root of variance of beta head, and the value of standard error of alpha head and beta head depends upon the error variance, that is some square errors, which is actually give you the kind of structure to report the T statistic of alpha head and T statistic of beta heads. So, in the next slides we will discuss how we will obtain all these standard errors for alpha head and beta head. So, once you get the standard error of alpha head and standard error of beta head, so we can get the T statistics for alpha head and beta head, then you can compare with the critical value, and this is the manual procedure or the kind of clarification how you have to obtain all these things and how you can validate the particular parameters so far as a statistical significance is concerned. Then all these jobs software can do for you, but it is mandatory that you should know how these are all coming and how this validation is happening. For instance, in this case, so these are all actually standard error for alpha head and beta head. So, here where I have reported here standard error of alpha head and standard error of beta head. So, ultimately the standard error of alpha head is reported here by software, and this is also for beta head. So, that means technically software will directly calculate standard error of alpha head and standard error of beta head. Then just you divide a alpha coefficient by standard error, you will get at the T statistic, that is T alpha, and then again standard error of beta head divided by standard error of beta heads, you will get actually T of beta heads. So, that means software already reported the alpha coefficient, the beta coefficient, the standard error of alpha, standard error of beta, and T of alpha head and T of beta head. So, ultimately when you compare actually calculated with it tabulated, it is a kind of systematic process. Of course, manually there is a standard structure. So, usually we check at 3 levels, 1%, 5% and 10%, and the signal is if the calculated value will overtake the critical value, then we can reject the null hypothesis, and in that context we can say that the particular parameter is statistically significant. So, first we start with 1%, because at 1% level the critical value is a higher one. Then if you could not reject the null hypothesis there, so you can come back to 5%, where the critical value is slightly lower compared to 1% level. Then again you check the calculated with the tabulated, then you have to see whether the calculated will overtake the tabulated, and if that is the case, then you can reject the null hypothesis there, and if you could not, then again you come down to 10%, where the critical value will be again lower compared to 1% and 5%. Again you have to compare the calculated with the tabulated at 10%. If that will cross the tabulated value, then you can reject the null. If not, then finally you have to conclude that the particular parameter is not statistically significant. But if you connect with the software will give you exact probability level where the particular parameter will be statistically significant, because these critical values are actually derived on the basis of simulation, and that is why when you put all these parameters and proxies, then automatically it will generate the probability values start with 1% to 100%. Since probability is between 0 to 1, so obviously the kind of significance levels will move from 0 to 1 only. So, accordingly, so the fourth columns it gives p values. So, where the alpha coefficient is also statistically significant and beta coefficient is also statistically significant, and that too at 1% level, and that too at the highest level. So, that means the first check of this particular process is the specification test, where we have to see whether the particular parameter is coming statistically significant or not. So, for that we have to take the help of t statistics and follow the hypothesis testing of t test, and then come with the kind of conclusion whether the particular parameter is statistically significant or not. And in this case we have to check alpha head and beta head, and for this problem and with this particular result well estimated output. So, we can come to the conclusion that alpha is statistically significant and beta is statistically significant. That means, technically so this model passes through the specification test, and after that we have to go for goodness of fit test, because it must be satisfied with all test. Then finally, you can declare that this model is a good ones and go ahead with predictions. So, then ultimately, so with this statistical output we can actually proceed for the kind of discussions. So, ultimately, so here the specification test structure which we have already discussed, that depends upon the standard errors which actually depends upon sum of the squares, that is nothing but the difference between y minus y hat squares, that is the error component, and this is what the formula through which actually we can get the sum of the error sum of squares of errors, and ultimately this will give you the kind of signal whether in a particular parameter will be statistically significant or not. So, usually lower the standard error, higher is the t alpha and t beta, and higher the standard error standard error. So, the t value will be lower. So, ultimately it depends upon again sum of the squares of the error, because the standard error component with respect to alpha head and beta head ultimately depends upon sum of squares of the error. So, technically for two variable case sum of the square errors, standard error of the estimates will be square root of sum of squares error divided by n minus 2. For three variable case it will be n minus 3, then for generalization case it will be divided by n minus k. So, ultimately, so this is what the kind of structure, and then we have to see how we can obtain this, and this is what the actual data, and we have already discussed this is x information and this is y information, and this is the residuals which is nothing but y minus y hat, where y hat not reported here, but we can obtain by putting or by using the estimated equations y hat equal to alpha hat and alpha hat plus beta hat x, and ultimately we will get the residuals, and after getting the residuals, so you can find out square of the residual, and that is the sum of the squares of the errors. So, in the last column, so this is the indication about the sum of the squares of the error, and so this will be give you some kind of structure to obtain the standard error of alpha head and beta head. So, ultimately the sum of squares error for this problem is coming 0.31, and ultimately standard error of the estimate will be coming square root of this particular component and divided by n minus 2. So, it is coming ultimately 0.1773, and the other part of this particular process is the goodness of fit test. So, here we have three items altogether, and that too y hat and error component. So, that means this is the actual and this is the predicted, and the difference will give you the error component. So, as a result, if you actually checking through variance factors, then you can find out the mean and then standardize it, and squaring both the sides, that will be give you the kind of structure here called as TSS equal to SSR plus SSE. So, SSR is called as a explained variations, or sum square regressions, and then SSE represents sum square errors. So, sometimes we can use ESS plus RSS, explained sum of square and a residual sum of squares. So, that means a total sum of squares, which is actually a summations y minus y bar whole square. This is called as total sum of squares, and which is equal to sum square explained, that is depends upon y head minus y head bar, and then the error component, which is the difference between the actual y and the predicted y. So, ultimately for any kind of problems when you use regression modeling, that to bivariate econometric setup. So, TSS always equal to ESS plus RSS or SSR plus SSE, that is sum of squares regressions and sum of squares error. So, that is otherwise called as a explained variations and unexplained variations. Explained variation will take care this part, and unexplained variations will take care this part, and the total will exactly equal to exactly equal to TSS, that is sum squares totals. In other words, you can write this one also SST, that is sum of square total, then sum of squares regression, sum of the squares error. So, now if you divide sum of square total in the right hand side, then it becomes 1. So, sum of square divided by sum of square total, and this is sum of squares again total. So, ultimately, so sum of square this is actually regression divided by sum of square total is called as percentage variation of independent variable to dependent variable, and this part actually called as a component called as R squares, that is called as a coefficient of determination, which is actually derived here. So, R square is the coefficient of determination, capital R square, which is the ratio between sum of square regressions divided by sum of square totals. So, then ultimately this will give you the signal where the fitness of the particular model. Usually R square range is 0 to 1. Okay. So, so the it is a kind of indication that what is the particular fit of a model. For instance, if R square equal to 1, then the model will be perfectly fit, and if R square equal to 0, the model is completely unfit, and if R square equal to close to 1, it is highly fit, and if R square is close to let us say 0.5, this is moderately fit, and if it is close to 0, it is very low fit. So, ultimately the structure of regression modeling depends upon goodness of fit test. So, goodness of fit test will give you the indication that what is the level of best fit. So, is it perfectly fit, that is 100% correct, or if it is lack of 100%, so maybe 90%, 80%, 60%, or it is a very low fit close to say 0 or 1%, 2% or 10% like that. So, it depends upon variations, and sometimes R square is considered as a good indications for the kind of prediction. The usual understanding is that higher the R square, higher is the predictions, lower the R square, lower is the prediction, or lower is the fitness, but this is not always correct. But in the first instance, if your model gives high R square, then the goodness of fit will be considered as a high, and if the R square is low, the goodness of fit to that particular model will be low. So, ultimately we have to see what is the level of R square. So, then the strength of the model depends upon this value of R squares, high or low or moderate, and then you have to go ahead with the kind of predictions. So, like in the specification test, we have alpha coefficient, beta coefficient, then you have to test alpha coefficient and beta coefficient to validate the model. So, the goodness fit structure is also like that. So, in the goodness fit test, the indicator is the R square, that is the coefficient of determination, which is the ratio between sum of square regression divided by sum of square total, and which will lie between 0 to 1, and close to 1 is a high fit, close to 0 is a low fit. And then we have to check whether the particular R square is statistically significant or not. Having high R square or having low R square is not so important, but what is important, whatever value of R square you will obtain from the process, that should be statistically significant. Compared to specification test, where the job is to validate the parameters or test the statistical significance of parameters, here the job is to validate the R square. So, whatever values of the R square in the model, so you have to check whether they are statistically significant or not. In the case of specification test, the test statistic which you frequently use is called as a t statistic, but in the case of goodness of fit test, so the test statistic which you frequently use is called as a F statistic, which is actually the ratio between explained sum of square and unexplained sum of square, and exclusively depends upon R square value. So, when R square is high and sample size will be very high, then by default high R square will lead to high F statistics, and if R square is low, sample size is low, then the value of F statistic will be also comparatively low. So, ultimately to validate this kind of parameters or this kind of scenario, so every times you must have high sample size, then there is a high chance that the particular parameters or the particular parameter with respect to alpha, beta, or F, R square will be statistically significant. So, now corresponding to specification test, where we have used t statistics, here we have to use F statistics, and the procedure of F statistic is more or less same like t statistics. In the F statistics, the first step is to set the null, that where let us say R square equal to 0, and then we have to choose this test statistic to validate R squares, and for that we have to consider every times F, and because this is the variance statistics, and then and R square is the variance indicator, and after using F statistic, you have to fix the probability level of significance at 1%, 5% and 10%. Then the decision making process will be the comparison between calculated F and then the tabulated F. The calculated F, which will derive through this particular formula, which will again discuss in the case of a particular table called as a analysis of variance. And in the tabulated statistics, the value of F exclusively depends upon the probability level of significance, that is at 1%, 5% and 10%, and the degree of freedom. Compared to t statistic, in the case of F statistic, we have 2 degree of freedom corresponding to some square explained and some square error term. So, then you have to get the critical value for F statistics, and in the other side we have actually calculated F statistic. Then we can compare calculated F with the tabulated F and check whether calculated F will overtake the tabulated at what level, 1%, 5% and 10%, and accordingly we can justify the significance of this particular indicator, that is the coefficient of determinations or the indication of goodness of fit. So, this is the standard procedure of goodness of fit test. So, in order to know more about this particular process, so let us move further, and this is what the coefficient of determination calculation. So, ultimately R square equal to 1 minus sum of squares errors, so divided by total sum of squares, and sum of square error we have already derived in the last slides, and just putting these ones, and then you will calculate total sum of square, which is the difference between sum of y minus y bar whole squares, and ultimately it is coming in this particular problem. this is coming exactly as 0.899, that means around 90%. So, the interpretation is that 90% of the variability of the cost of flying a airline is accounted for by the number of passengers. So, that means this is actually most important and significant variable which can lead to the determination of airline cost. So, as per the theoretical kind of understanding and kind of logical hint, so the empirical results are also supporting and validate the particular hypothesis. So, ultimately, so this is the kind of structure. So, this is what actually the R-square indications, and this is what the kind of parameter specifications, and that too we have already discussed with respect to the Excel regression output. And ultimately, so this is for actually this is for beta coefficient. Then this is accordingly means standard error for beta coefficient, and then ultimately the degree of freedom is calculated to its size is 12 and n minus 2, that will be coming actually 10. Ultimately, these are all actually manual understanding. The software is already obtained these results and then compared and also declared the statistical significance of these parameters, and that is the probability at what level of probability these parameters are statistically significant. And ultimately, this is the procedure through which you actually justify the importance of these parameters alpha hat, beta hat and R square. Till now we have gone through the specification test and goodness fit test, that to validate the regression equations or regression line with respect to all these parameters alpha hat, beta hat and the coefficient determination R square. And the test procedure also we have discussed, that is with respect to T test and for the specification test and the F test for the goodness of fit test. And by using all these kind of structure and for connecting to this particular airline problem, so both the parameters are statistically significant and goodness of fit also showing statistically significant. These are all we have already discussed, and this is what the F statistics, and it is also coming actually statistically significant. Okay, so as a result, this is okay. So this is 4.96, and ultimately the F statistic is coming. This is this is tabulated actually. So 5% and a degree of freedom 1 and 1 and 10. So this is how the indication through which actually you derive the F tabulated. So the n is the sample size, k is the number of parameters, and then finally we can obtain this particular structure. So here is the final results how you have to obtain, and ultimately the F value is actually coming 89.09, that is the calculated, and the tabulated which we have here is 4.96, and if the calculated F is greater than to this tabulated value, we can reject. If the calculated F is less than to tabulated, then we cannot reject, and accordingly if you go through this particular final output, then the F is coming actually 89.1, so which is actually very high compared to the tabulated value 4.96. So as a result, we will reject the null hypothesis, and we will come to the conclusion that so this model is okay with the goodness of fit test and the specification test. So with this we will stop here, and we will continue this discussion in the next lecture. Thank you very much.